Hey guys, today we will be going into a thing called hypothesis testing. So the basis kind of scenario that you'll see hypothesis testing used on is what we have here. So let's say a cereal company claims that 30% of their boxes have a toy inside, and then you go and you take 50 boxes from a store, and we find that only 23% of those boxes have a toy. Does this mean that the company was lying, or did this happen completely by chance? So the way that we introduce sampling distributions into this kind of problem is if you look at, again, our sampling distribution graph, and then you'll remember that whenever we keep taking samples, our samples will fall into a normal distribution around the true proportion. So if the company tells us that our true proportion is P, this will be our P company. What they say may be true and might not be true. This is up to us to decide. So the company said that the proportion of boxes with toys is 30%. So our P company is 30%. But when we went and we got our sample of boxes from the store, only 23% of them had toys in them. So that's something out here, right? There's some data point out here in the normal model. So what we want to find is, does it make sense for us to have a point out here? Is that possible by chance? Or are they lying, and is the true distribution somewhere out here, lower than the company reports? So is the P centered around a different value rather than the one that the company reports? So that is the purpose of hypothesis testing. Hypothesis testing is when we see whether or not our true proportion is what it seems to be, or if it's some other value. So to give an overview of hypothesis testing, what we do is basically we list out what the company says is the case, and then we list out what would happen if the company was lying, and then using those guidelines, we do some math, and we get back a probability. That probability tells us if the company wasn't lying, then what is the probability that only 23% of our boxes had toys when the company said it was 30%. And then we decide if that probability is too small, then we're going to say that the company was lying, because we got something that really looks like an outlier, so this doesn't seem like something that would happen if the company was really telling the truth. Putting that into an actual procedure, we have 4 main vocabulary words here. The first one is our null hypothesis. This is our original assumption, and this can never be proven to be true. You can only prove a null hypothesis to be false. You can think of this as like in criminal law, when a person is innocent until proven guilty. A null hypothesis here would be that the person is innocent, because that is our original assumption. Before we look at any other evidence, we assume them to be innocent. And then if there's enough evidence against them, then we decide that we no longer want to go with a null hypothesis. We are going to change to the alternative that they are guilty. So your null hypothesis can be contradicted, but it can never be proven true. You can't really prove that someone is innocent, you can only prove that they are guilty. Your alternative hypothesis is your conclusion that you will draw if the null hypothesis is not true. So if someone is innocent as our null hypothesis, then our alternative hypothesis, if they're not innocent, is that they are guilty. Or if our null hypothesis is that the company is telling the truth, then our alternative hypothesis is that the company is not telling the truth. You cannot prove that the company is telling the truth. You can only bring up evidence against them to decide whether or not to reject that original assumption. Next, you have your p-value. The p-value is the number that you get from your math that tells you the chance that your observed data happened by chance. If the null hypothesis is true, then the p-value is the probability that our observed sample data happened completely by chance. And then we have an alpha value. So the alpha value is a sort of probability threshold. If we go below the alpha value, then we decide to reject the null hypothesis. So we take our p-value and then we compare it to our alpha value. So if our alpha value is greater than our p-value, then we decide that the p-value is too low, and then we are going to reject the null hypothesis. Normally, we will set our alpha value as alpha is equal to 0.05. So if we get from our hypothesis testing that there is a less than 5% chance that the observed data happened by chance, then we reject the null hypothesis. So if our p-value ends up being 0.02, We see that 0.02 is less than alpha, which is 0.05, so we decide to reject the null hypothesis in that case. So here are the steps for our hypothesis test. I will go into detail with each of these in a minute, but this is your general overview. The first thing you always do is list out your hypotheses, so your null hypothesis and your alternative hypothesis, and then all of your important numbers. So those would be your p-hat, your alpha, and then your sample size. Then you check your conditions. I will go into what those are in a minute, but some of them will look very, very familiar. Then you will need to calculate a standard error and a z-score for your model. And then using the z-score that we get out of the math, then we will draw a normal model and flag our z-score, and then use the calculator to get our p-value based off of the z-score. And then using the p-value, we will conclude whether or not we reject the null hypothesis. It sounds a little crazy right now, but it's a lot simpler than it looks. So the first thing that you do is list out everything. So here's an example. A company's juice dispenser overfills bottles 12% of the time. You try the dispenser 50 times and it overfilled the bottles 16% of the time. Is the juice dispenser overfilling a different proportion of times than 12%? If we said before that the company's juice dispenser overfills bottles 12% of the time, but when you went and you tried for yourself, it overfilled way more than that, it's asking, did this happen by chance? So what is our null hypothesis and what is our alternative hypothesis? So your null hypothesis is that everything is as is. Your null hypothesis will always be the status quo. So you will say that the company's juice dispenser overfilling rate has not changed. It is exactly what the company said. So no change, keep the status quo. So our null hypothesis, which is denoted with an H0, would be that your P, so your population proportion, is equal to 0.12, keeping the status quo. Next we have our alternative hypothesis, or H sub A. What will we decide if the true proportion is not 12%? If you look at the question, it says, is the juice dispenser overfilling a different proportion of times than 12%? So it's only asking if P is not equal to 12. So that is our alternative hypothesis. P is not equal to 12. Note that for your alternative hypothesis, it will never be P is equal to something. The only ways that you can write your alternative hypothesis is P is less than, P is greater than, or P is not equal to. These are the only three ways you can do it. You will never have a direct assignment of probability. It will always be one of these three. In this case, because it said different, then that doesn't specify a direction less than or greater than, so we just go with not equals. But if it said, is the juice dispenser overfilling more proportion of times than 12%, then we would go with P is greater than 0.12 because the question has now specified a direction. Now we have our alpha value. So the thing with the alpha value is that if the question does not specify, then you can directly list your alpha value as 0.05. If it specifically says alpha value of 0.02, then just put alpha equals 0.02. But most questions don't say anything, so they're completely fine with you just leaving it as 0.05. Now, there's some other important numbers that you need as well. So you need to give a p-hat and an n for a sample size. So your p-hat, if you'll remember, is the data that you got from your sample, not your population proportion, your sample proportion. So this is when you went and you tried the machine. So that would be 16%, 0.16. How many bottles did we fill to see if the dispenser was overfilling? So we tried it 50 times. That is the number of trials that we ran, and that is our n. Next we have our conditions. These should look really, really familiar again. First is our independence condition. So does one bottle being overfilled have anything to do with another bottle being overfilled? Then we have randomization. Was a random sample taken? One more thing about the randomization condition. If the problem does not specify that the sample was randomly taken, you can't just stop there. Your goal is always to continue through the conditions. You have to think for a minute. The point of randomization is to ensure independence and representativeness. So if your sample wasn't random, then it wouldn't be representative of the population, right? So if you want to still somehow BS your way through your randomization condition, but the question doesn't specifically say that the sample was random, the best way to BS it is say something along the lines of this. Although the sample was not randomly taken, we have no reason to believe that the sample is not representative of the population. So we have no reason to believe it is representative, but we also have no reason to believe that it is not representative. Next, we have our 10% condition. So did we sample under 10% of the population? Always think big for your population. So for our company juice dispenser question, did we sample under 10% of the juice bottles that the dispenser will ever fill in its entire time operating? Then we have our success failure condition, aka our large enough condition. So this one says that our NP has to be greater than 10 and our NQ is greater than 10. So this is a really easy thing to get confused because now in our question we have our P from the null hypothesis. So for the juice dispenser question, we said that P is equal to 0.12, but then we also listed out a P hat as 0.16. So you'll think, which one are we going to use for the success failure condition? So again, it's like in a court of law, you go with your original assumption. We always assume that they're innocent until proven guilty. If we're assuming them innocent, then we're just going to believe that the null hypothesis is true until we get to our conclusion, so until we get our p-value. So if we assume that our h0 is true, then we are going to use this value of p for our success failure condition. So we will be using the 0.12 for our NP is greater than or equal to 10 and our NQ is greater than or equal to 10. Don't use your p hat. What you need in your next step, this is all of your math now, and the main point of this is to get a z-score to put onto the normal model. So why the normal model and why z-scores? If you think about it, given our population data and then given our sample data, if we look and see that our sample data is really extraordinary compared to what the actual population proportion is supposed to be. So if the company said that 30% of their cereal boxes have toys, but when we went and sampled, only 1% of our boxes have toys, something looks to be really wrong, right? So what we're doing is we're taking our P as the center of our normal model, and then if we get a point out here, then that's going to be really extraordinary, right? So we're going to calculate our z-score because the point of a z-score is to tell you how extraordinary a data value is, so how many standard deviations off from the center it is. So to calculate our z-score, we need three things. We need our p-hat, our p, and our standard error as listed over here. We have our p-hat as given in the question. We have our p, this is what we say p is equal to in the null hypothesis, but we do need a standard error. So your standard error needs to be calculated before your z-score, and it is equal to the square root of pq over n. Notice that I did not use p-hat and q-hat because we're always going to use our null hypothesis numbers as our calculations. Our p-hat will only be used when calculating the z-score. So if we say in the null hypothesis that p is equal to 0.12, then our p up here is going to be 0.12 and our q is going to be 0.88. And then our n is still just the size of our sample. So now that we've gotten our z-score, we need to draw a normal model based off of our z-score. First of all, you know that your z-score is based on the standard normal model. So you will draw a normal model with the mu of 0, and then you will mark off where your z is. So if our z-score was 1.2, then we would do mu 0, put a 1 somewhere over here. It doesn't have to be accurate. And then we give a rough estimate of where our z is, and then we flag it. So we have flagged our z. So what do we need to find now? Well, we want to know the probability that our sample data happened by chance, right? This flag is now representing where our sample data is on the standard normal model. So we want to know the probability that z or any more extreme values occur. So anything from here to here occurring. What is the probability of that happening? You will take your z and just go to the closest extreme. So for this z, this one is closer to the positive end of the graph. So we go from z to infinity. But instead, if our z were out here instead, then this is closer to negative infinity, so the negative extreme, than the positive extreme. So we will shade in our graph this way. So we've drawn out our normal model, and then we know which part of the graph we're looking for. You'll remember that there is a calculator function that gives us back an area of the normal model based off of a z-score. So that is our norm CDF function. For this case, we will leave mu as 0 and sigma as 1. And then based on our normal model, we will put in a lower bound and an upper bound. So for our normal model from earlier, we had 0 and then z was equal to 1.2. So we would write 1.2, flag it, and then shade in the area that we're interested in. So this is a range of values that we can put into the calculator. The range of values has a lower wall at 1.2, so that is our lower bound, and then it goes all the way up to infinity. So our upper bound is infinity, with a mu of 0 and a sigma of 1. By the way, some calculators don't take the actual symbol infinity, but if you just spam 9s, then it'll still count it as an infinity. It'll give you back the right numbers. But you'll remember there were some special terms that we had in our original problem. So the problem said, what is the probability that p is different from 0.12 versus other cases of what is the probability that p is less than 0.12 or p is greater than 0.12. Those are very, very different questions. So we have to take into account the wording of the problem. So we had 3 kinds of alternative hypotheses: that p is not equal to some number, that p is less than some number, or p is greater than some number. So both of these show direction, right? In this case, if we were calculating the probability that p is greater than some number, then we would just be calculating this area because we're calculating the probability that p is equal to this number or greater. The same thing for our second option. So if we were calculating the probability that p is less than some number x, if we flagged the z-score for that value, then we would just calculate the probability that any value is here or less. But what about not equals to? If we say that x is not equal to y, that means that y could be less than x or y could be greater than x. So here, we're not just looking at the negative direction or the positive direction anymore, we're going to be looking at both directions. So we have to add up the probability that it's in the positive direction and the probability that it's up in the negative direction. So for a not equals to question, if we got some z-score over here, when we draw our normal model, we'll still list it off in this way. We will shade it from z to the extreme, and this is the area that we're looking for. However, we're also interested in the negative side too. So then we can't just mark off the positive z, we also have to mark off the negative z, because we're looking in 2 directions now. This is a 2-sided test, and we look for this area as well. One thing you'll remember though is that your normal model is always symmetric, perfectly symmetric actually. So that means that the area over here is equal to the area over here. And therefore you won't have to separately calculate these 2 areas. All you have to do is get this one area and multiply it by 2. So when you draw your normal model, you can just leave it at this and only shade in the positive side, but when you actually put in your calculator language, you will add an extra 2 times up here. So 2 times your norm CDF probability. And then out of that, you will get some probability finally. So that will be your p-value. So now that you have your p-value, you need to conclude. So what we're saying is, what does the p-value mean? And then based on the p-value, do we reject the null hypothesis or do we fail to reject the null hypothesis? You have to be really, really careful with your wording here, because you'll remember again, we can never prove a null hypothesis to be true. We can't prove someone to be innocent. We can only provide evidence that they are guilty. It's like talking about aliens. If I ask you, do you believe in aliens? Depending on which one you choose, let's say you don't believe that there are aliens. Can you prove that there are no aliens? You can't go to every celestial body in the universe and go check, hey, are there aliens here? However, all it takes is one celestial body with alien beings to disprove your null hypothesis. So here, you cannot prove your null hypothesis to be true, you can only disprove. So we can only reject the null hypothesis or fail to reject the null hypothesis. This is why, again, in criminal law, we only say someone is either guilty or not guilty. They do not declare people innocent, they declare people not guilty. So the way you would write out your conclusion is like this. So the first part you can copy word for word basically. If the population proportion were truly equal to, and then insert your p, the probability of the observed data occurring would be insert your p-value. Then you make a comparison of your p-value to your alpha. So because our p-value of 0.02 is so small compared to alpha, which is 0.05, then you decide whether to reject or fail to reject the null. So we would reject the null if p-value is less than alpha. We fail to reject the null if the p-value is greater than alpha. It's a very neat, clean binary decision. So that's a lot. Here is a final practice question, a full-blown hypothesis test. So a factory reports that 11% of their products are defective. When we check 200 of their products, 14% are defective. Is this evidence to believe that their defect rate is higher than reported? So what is our step number 1? Our step number 1 is listing out our important numbers and our hypotheses. So it doesn't really matter which one you put first. I personally prefer putting our important numbers first. So first we need to put down our p-hat. So what is our sample proportion? What did we get from sampling their products? That's when we personally went and checked, so that is our 14%. Then we need our n, so that's our sample size. How many did we check? We checked 200. Those are our two important numbers. Now we need our null hypothesis and our alternative hypothesis. So our h0 is our original assumption. We're going to keep the status quo for our null hypothesis. So that means we're just going to believe that the factory is innocent. They did not lie to us about their defect rate. So we believe that their p is exactly what they reported, 0.11. Now we have an alternative hypothesis. So what if they are lying? We have a choice here between not equal to, less than, and greater than. Which one do we choose? So this decision lies in our last sentence. Is this evidence to believe that their defect rate is higher than reported? Higher than reported. So the question has given us a direction, and they're asking basically the probability that p is higher than 0.11. So this is the one that we choose. P is greater than 0.11. Next we have our conditions. So this is where it gets to a lot of writing. First we have our independence condition. Does one product having a defect affect whether another product has a defect? This is very debatable because you could just have one really bad machine that's just sitting there and then churning out a bunch of really bad products. So we don't really know if it's independent or not. We don't have evidence to believe that it is independent, but we also don't have evidence to believe that it is not. So what we do here, again, this is really great practice for a more realistic question where you don't have a perfectly random sample, or you have some cases where it's a little iffy on whether or not it's really independent. So how would you talk about independence? Well, you can't just lie and say that there's definitely no problem. You have to acknowledge the faults of the problem. So you have to say what the problem is, and then you're going to say, here's the problem, but we don't have any evidence to believe that it's not independent. So we're just going to go ahead, but please remain cautious. Although faulty machines may lead to a loss of independence between products, we really don't have any evidence to believe that there has actually been a loss of independence, so we will proceed with caution. This is your most important phrase here, proceed with caution. Next we have randomization. The sample was not randomly taken. The question does not say the word random, so we will say, again, my sentence from earlier. Although the sample was not randomly taken, we have no reason to believe that the sample is not representative of the population. Next we have our 10% condition. So is 200 less than 10% of all of the products the factory will ever make? Considering your modern day factory, the answer is yes. 200 products is surely less than 10% of all products that have and will ever be produced by the factory. And then finally we have our success failure condition. So NP is greater than or equal to 10 and NQ is greater than or equal to 10. Writing that out, we have to show all of our math so it ends up looking like this. Because NP, which is equal to, substitute in your numbers, 200 times 0.11, which is what we said in our alternative hypothesis, is equal to 22, which is greater than or equal to 10, and NQ, which is equal to 200 times 0.88, is equal to 178, which is also greater than or equal to 10. The sample is large enough to apply the CLT. So this basically means we're going to use a sampling distribution. We are going to use the normal model here. And then finally, since we have passed our conditions, we have to conclude and say, yes, we passed the conditions, and next we are going to run a hypothesis test. So because conditions are satisfied, so yes, we passed the conditions, we can proceed with a 1 proportion z-test. So that is the name of the hypothesis test that we are performing here. We can break this down into 2 parts. 3 parts actually. So first of all, how many samples did we take? We only took 1 sample of 200 products. So that's where our 1 comes from. In all of statistics, we will really only be working with either 1 or 2 samples. And then next is the question about proportions or means. So we know that it's about proportions because we see a percent sign here. So 1 proportion. And then we have 2 kinds of tests. One is called a z-test and one is called a t-test. Your z-test will go with proportions always, and then your t-test goes with means. We also call it a z-test because in the end, our ultimate goal is to find that z-score. So we can go on to step 3 now, which is finding our z-score. So the formula for our z-score is this, p hat minus p over the standard error of p. So we know that our p hat is 0.14, that was given in the question. We also know our p, that was part of our null hypothesis. What we do not know is our standard error for p, so that is actually the first thing that we should be doing. So here's our formula for the standard error of p. What we have to do here is just plug in our numbers and we can go. So the square root of 0.11, because we always go with the null hypothesis assumption, not our sample. So our p, which is 0.11 times q, so that's 1 minus p. Because q, again, is always equal to not p, or 1 minus p. That would be equal to 0.89, and then our n, our sample size, is 200. Putting that into the calculator, we get a standard error of 0.0221. Now we have all 3 numbers that we need to calculate our z-score. So our z-score is equal to our p hat minus p over the standard error, which is equal to, plugging in everything now, 0.14 minus 0.11 over the number we just got. So 0.0221. And that is equal to 1.35595. That is our z-score, and we have finished with step 3. Our step 4 now is to make a normal model based off of our z-score. We can just draw that off to the side there. So we have a normal model, very rough drawing. Again, it doesn't have to be perfect. Since z-scores are based off of the standard normal model, we label our mean as 0, and then our standard deviation as 1. Here is where our z-score approximately is, so we mark off 1.356. And then again, we always go from our z-score to the nearest extreme, so that would be the positive extreme. And then we know that since our hypothesis is only one-sided, we didn't use not equal to, we used greater than, so we don't have to multiply by 2. So now we can go on to step 5, using our calculator. So we have to say the probability that z is greater than 1.356 is equal to, and then we put in our calculator function. Norm CDF, and we give a lower bound, an upper bound, and then we already know since it's a z-score, we will be working with a mu of 0 and a sigma of 1. Now, what is our lower bound and our upper bound? We can get all of that from our normal model drawing. Since our area is from 1.356 to infinity, that's exactly what we put in for our lower bound and our upper bound. We start from 1.356 and then we move upwards to infinity. Putting that into a graphing calculator, we end up getting a probability of 0.0876. So now we have our p-value. Our p-value is equal to 0.0876. So what does this mean? We can say that now in our conclusion. So the first thing we say is, what is our p-value and what kind of context is it in? So using as much context as possible, I said, if the true proportion of defective products is equal to 0.11, the probability of the observed data occurring is 0.076. So the probability of our 0.14 happening by chance is 8.76%. And then now we say, using our p-value, are we going to reject the null hypothesis or fail to reject the null hypothesis? So this is where we make our comparison with our alpha value, which is 0.05. Because the p-value is so large, and then I made a comparison with the actual numbers. So 0.0876 is greater than alpha, which is equal to 0.05. I failed to reject the null. If you want, you can even add in an extra sentence that says, we do not have enough evidence to believe that their defect rate is higher than reported. Case closed. And that is the end of a hypothesis test. So thanks for watching. Hope you learned something. Peace.